Hi, my name is Ali Shirsavar, and over the next hour or so I'm going to talk to you about digital power. We're going to talk about this new technology, its advantages and its disadvantages, and whether or not this new technology is suitable for your application. Let's have a look at a traditional analog power supply, and then we discuss how a digital power supply differs. What you can see here is an analog power supply. Around here you've got the power stage, then you've got an analog controller which controls the PWM switch, which is around here. Now, in analog world, we have got the advantages of high bandwidth, high resolution, you've got low cost. The theory is really well understood. There are lots of application notes and books and lots of good videos. There are a lot of experts out there that can help you. But as with everything else in engineering, it's got a certain number of challenges. You need lots of components. Your manufacturing cost, therefore, is higher. You need a bigger PCB area because you do have lots of extra components. And your mean time between failures is not that good, again, because there are a lot of components. Now, component drift, aging, and tolerances impact an analog power supply much more so than a digital one, because the control loop in an analog power supply is designed around an op-amp with capacitors and resistors and so on, whilst in digital that becomes a couple of lines of code. It is hardware based and therefore it's not very flexible. By that, what I mean is once you have soldered the values in order to make any changes, then you need to get a soldering iron out and you need to change things. Whilst in digital, you can easily change the control loop performance within software. It is limited to classical control theory, and therefore you cannot apply advanced and sophisticated and nonlinear control methods. And there is no intelligent control over the performance. Whilst you have designed it, although there are some aspects that you can do, like when the load drops, you can go into burst mode or pulse skipping mode. Beyond that, there is very little you can do. Whilst in digital, again, you can change the performance of the power supply in code. So what you can see here is a typical digital power supply. This is the plant, which is still analog, big inductor, big capacitor. We're showing this in this part of the block diagram. And then you have got the ADC and the PWM, which are implemented inside of the MCU's hardware. So what actually will happen is that you sample the output and then you send that into a Z-domain controller, which is part of the software, and then that drives the PWM, and then the PWM drives the plant. And this is implemented inside of the MCU. So all we need to do is set up some PWM, some ADC, and program the Z-domain control algorithm into the chip. Now, there's a great deal of help from Biricha to allow you to do this. There's automatic design software called Biricha WDS. It's a very sophisticated piece of software that designs digital control loops. We've got software libraries, we've got in-depth hands-on workshops from various vendors in digital power, digital PFC. We even have an analog power supply design workshop. And then there are lots of application notes and design guidelines on our website. So, benefits and future of digital power. Okay, so what are the advantages of digital power? Well, there are three main categories that I would put them into. One is the ability to combine multiple control loops or functions into one device. You can eliminate a whole bunch of components, you can reduce manufacturing costs, you can get one device and multiple or variable outputs. I had one particular client who manufactured a range of power supplies, and let's say you had 50 watts, 100 watts, 500 watts and a kilowatt. Now, if you want to make these in analog, each one of these would have to have a dedicated integrated circuit. Each one of them would have to have a dedicated control loop, which is based on capacitors and resistors around this. And therefore, you have to buy lots and lots of different components in order to make this range of power supplies. What he was trying to do was to rationalize the number of components that he was buying. So he bought a microprocessor, and he used this microprocessor to control the 10 watt, the 50 watt, the 500 watt, and the 1 kilowatt one. And very few components needed to change because the control loop was in fact part of the software. As you can imagine, you can also have variable outputs. because you can change the control loop performance, you can have, for varying input voltages, you can change the parameters within the software and get a variable output whilst still maintaining the loop performance constant. And that is very difficult, if not impossible, to do in analog. And by reduce real estate, I mean that you reduce the size of the PCB. If you have got many power rails and you want on one board and you want to do this in analog, each one will need to have its own dedicated IC, each one will need to have a bunch of capacitors and resistors around it for the control loop, and then you have to route this stuff, and routing becomes very, very difficult. You have to have many layers and so on. So by going digital and just using one microprocessor, because you eliminate all of these components and these become a few lines of code, you can actually reduce the size of your PCB. Then there's a flexibility of software programmable solution. You can have advanced and nonlinear control in order to improve the performance. For example, many of you are aware that as the output capacitors on a power supply dries up, the size of the ripple will increase because the ESR of the capacitor will increase. Well, if it gets large enough, you can try and look at the size of the ripple in digital and have some failure protection in place. There you can have communications. These days, most MCUs come with lots of different communication ports, so you can have communication perhaps with other devices, and you can have auto-tuning, self-tuning, and self-commissioning. Again, the microprocessor can run a certain algorithm at the beginning in order to try to evaluate the certain parameters within the power supply and then tune the power supply loop on its own. And in fact, we've got a demo of this whereby the microprocessor automatically tunes the control loop, and we're going to demo that in a little bit very shortly. And then, of course, there is power-ups sequencing. Many sophisticated chips these days require many rails, and they have to be powered up in a certain sequence at a certain rate and powered down in a certain sequence at a certain rate. Again, in analog, that is very, very difficult to do, whilst in digital, it's again a matter of putting a few lines of code in place in order to do that. Looking at these, so you can add these advantages together and effectively reduce the cost, and it also reduce the size of your product. Again, I had an experience with one camera manufacturer whereby he needed power management for the battery charging. Then he needed 3.3 volts and 1.8 volts for various rails inside of the camera. And then he also needed to boost the voltage up in order to drive the flash gun for the camera, and everything had to fit in a very, very small box. You can see that digital lends itself to this sort of application very well. Then the third category is the ability to meet the ever-increasing efficiency, environmental safety, line harmonic, and EMC regulations. Now, this trend will continue, and the regulations are only going to get more and more difficult, mainly because of the environmental and energy price issues. So we have seen now many standards that you have to apply, the titanium standard. For example, in order to give you a very high performance in terms of efficiency over a very wide load range. And that is very difficult to achieve with linear control that you get in an analog chip. You invariably will have to change the performance as the load changes in order to make sure that you get high efficiency in order to meet these new regulations. You can have software control of standby power. So when your unit goes into standby, you can put everything to sleep and basically shut everything down so that you draw very little current, and as soon as the user reactivates the device, then everything can wake up. So you can get much better consumption and on the standby. Then you can change modulation strategy for better efficiency. We do that right now in analog control, whereby at low loads, what happens is that you try to reduce the switching frequency. As you can imagine, I need to draw this on the board for you. You've got your PWM, and at low loads, it is very, very small. So You don't need to be switching this fast. This is time here, and this is the width of the PWM. So what you can say is that, well, instead of switching, let's say, every 5 microseconds, that would give you a switching frequency of 200 kilohertz. You can say, well, at low loads, I don't need to do that. So I can actually delete this one. And let's say delete that one. Then from here to there, that will be 10 microseconds. Therefore, my switching frequency will be 100 kilohertz, and I reduce my switching losses. You can do this in analog, and you can do this in digital. The difference is that in analog, your control loop stays the same. Now, if you have designed your control loop to be regulating with a switching frequency of 200 kilohertz, that's 5 microseconds, and then suddenly you skip this pulse in the middle, you end up with an extra time delay, a pure time delay, e to the minus st in your transfer function. Now, this could cause havoc with your control loop. In all fairness, this is in low load, so hopefully nothing will go wrong. But what you have done effectively is you have added a pure time delay into your control loop. However, in analog, you are not capable to change the control loop performance. In digital, what you will do is as soon as you skip this pulse, you also change the control loop performance in order to make sure that now the control loop expects 100 kilohertz switching frequency as opposed to 200 kilohertz. You can have intelligence phase shedding under low loads. Again, this is one of those efficiency requirements. Power supplies typically perform very poorly at low loads in terms of efficiency. So instead of, let's say, designing a 1 kilowatt power supply, you can design 2 500 watt power supplies and turn them on as the load goes up each stage and turn them off as the load goes down. This, as you can imagine, on the software control is a lot easier than on the analog control, and also you can choose the number of phases. You're not tied to an IC that is capable of doing, let's say, 4 phases, or having to put 4 different ICs and daisy chain them together with an enable signals. It all happens seamlessly in software. So if you imagine you've got a 4-phase interleave power supply, as the load goes up, the software will automatically turn phase 1, phase 2, phase 3, phase 4, and as the load goes down, you shed the phases. So you go phase 3, phase 2, phase 1, and so on. And the net result is that you get much better performance in terms of efficiency under low loads. Then you can have spread spectrum techniques. Now, again, the spread spectrum techniques is interesting because we do this in order to pass the EMC test. You are trying not to have a massive spike at the switching frequency or harmonics of the switching frequency that goes above the allowable limits. And a way of reducing the height of the spike is that instead of having a fixed switching frequency of, let's say, 200 kilohertz, you vary the frequency, let's say, from 190 to 210 at a certain rate. Now, again, in analog, the way this is done, let's say you have 200 kilohertz here. Let's say you have 210 kilohertz here, for simplicity, and let's say you have 190 kilohertz here. And now typically how this is done in analog is either with a sawtooth function, so you go from 190 to 210 in this manner, or as a sinusoidal function, typically a sawtooth. Now the frequency at which you go from this point 190 to that point 210 will be much lower than your switching frequency, and that this will get through your control loop and you will end up with an unwanted ripple on the output. What you really want to be doing is that instead of having a linear function, if you, instead of ramping from 190 to 210, you want to have random switching frequencies so that the actual change in the switching frequency is a random function, or at least a pseudo random function, and therefore you don't end up with a ripple on the output. So you can do this in digital, although it is possible to do it in analog. In digital, you can do it much better. Software programmable harmonic filtering for PFC. Well, for those of you who design power factor correction units, again, this is a requirement for anything above 75 watts. You need to reduce typically the second harmonic of the line frequency. Now, line frequency changes from country to country. In Europe, we run at 50 Hertz. In the United States, at 60 Hertz. So if you're designing an analog filter, even if it's a simple RC filter, you have soldered in the components, the R and the C. And therefore, the performance of the filter will change. Whilst in digital, you can detect the line frequency, and because the filter is done in a line of code, you can easily change the performance depending on which country you plug in your power supply. We've done that. So to conclude then, digital power will play a very dominant role in the future of power market, and early adopters of this technology will reap the reward of the investment in digital power. So now I'm going to do a quick demo for you. What we have got here is a little microprocessor board. This is a TI-C2000 Piccolo microprocessor, and it's attached to a tiny little power supply that we have designed. That has got no intelligence of its own. It is simply just a power stage, and the microprocessor is going to control it. And if you remember earlier on, I said that we're going to make this self-tuning, and I will show you how this is done in a moment and as I run the software. So first of all, I'm going to plug this in. It is looking for the hardware. It has found it. It is opening the COM port. And now it is actually running. So what we have here is a little power supply with the output voltage of 1.8 volts and the switching frequency of 200 kilohertz. Okay, now have a look at these coefficients over here. These coefficients are the control loop's coefficients, and have a look at what happens to these coefficients as I change the switching frequency. If I change the switching frequency, you can see that the coefficients change automatically, and the reason for that is that the software is automatically tuning the loop. I can add some load on, and you can see tiny amount of ripple. We'll demo this in a little bit later, but to show you that in fact the switching frequency is changing as I do that, I can also change the output voltage. We're going to turn the oscilloscope on and show you the actual switching frequency change and the output voltage change that is happening automatically whilst the loop is being retuned. So I'm just going to turn over and I'm going to show you how this works in real life. That's the ground, and that should be my gate drive, my switching frequency, and I should be able to see that on this monitor over here. So let's do auto set and see what we have. That is on channel 2. No. We need to... Oh yes, I know what's going on. Okay, let's add some load so that we actually have some PWM. There we go. And I'll turn off channel 2. Okay, so here you can see the PWM that I have got. I'll see if I can increase the intensity of this so that you can see it better. We're going to link to a computer in a minute, and okay, I'm going to make it a little bit brighter so that you can see it over here, but this actually got a web interface, so we can actually connect to the web interface and have a look at exactly what's going on. For now, if you have a look at this, this is showing you the switching frequency of the power supply. If I do a quick measure, you can see that the frequency is 173 kilohertz, and 173 kilohertz happens to be exactly what I have set it to. So 170, you can see it on the computer screen. And if I change that, you should see the change over here. So I'm going to increase the switching frequency here from my automatically, I'm going to use this slider and go from 170 kilohertz, and I'm going to move the frequency out to around 400 kilohertz, and you'll see immediately, you can see that the switching frequency is now 400 kilohertz. The interesting part is that the power supply is still stable, and the reason is that if you have a look at the screen, you can see that as I change the switching frequency, the control loop parameters actually change. The output voltage is set to 1.35 volts. You can see on the oscilloscope that it's 1.35 volts. If I turn on channel 2 and connect channel 2 to the output voltage, you can see that this oscilloscope is measuring it around 1.49 volts. Over here, it is set to 1.35. If I increase the output voltage, you should see, there we go, I can increase that on my slider on the software, and as I increase that, you can see on the oscilloscope, the output voltage changes. Again, the important part to note is that as I am changing this output voltage, my controller parameters are being retuned. So you are not losing control over the control loop. The control loop constantly is retuning itself. Okay, very good. So the other few things that I can show you right now, as you can see, you've got a little oscilloscope here on our own. That's a lot quicker to do it on this for this simple test. I do apologize for the bottom. What has happened is that because of the resolution of the screen, we have kind of lost the scale. But let me set this to load step. You can see that you've got a load step over here. If I set it to AC coupling, this one is just for the oscilloscope trace, the x-axis. So you can see that this is the loader step that I'm getting. Now I can store and display this. Note that the axis here is the scale is very, very fine. I can store and I can display. The green trace now is the actual oscilloscope, the loader step for this 390 kilohertz, 5 kilohertz bandwidth. So I can change the crossover frequency. Again, please have a look at the control loop parameters, and you can see that as I increase the crossover frequency, the transient response changes. There you go. You can see that you've got a much better transient response because now I am crossing at 16 kilohertz and not at 5 kilohertz. Now we know from our control loop courses that if your crossover frequency is very, very close to your switching frequency, then the power supply will go unstable. So if I reduce my switching frequency to 50 kilohertz and then increase my crossover frequency to 20 kilohertz, you will see that the power supply is actually unstable. You can see that it is oscillating. And then you can turn around and say, well, you know, I don't like unstable power supply. So what I can do is I can increase my switching frequency a little bit, and I can reduce my crossover frequency a bit more. And hey, there we go. The power supplies are stable again, and I've got a very nice transient. Now, in analog, this could simply not be possible without removing literally hundreds, if not thousands of components. You calculate the value of the compensator components, you desolder them, you resolder them, and you do the test again. We have just completely retuned the power supply from utter instability to nicely damped and stable, and we've changed the switching frequency and the crossover frequency and the output voltage. And we have shown on the oscilloscope as well as here on the software that the power supply self-tunes and it is stable. What you just saw was an example of a self-tuning, auto-tuning power supply. What we have done here is that we have taken a mathematical model of the power supply, its transfer function, and we've put this mathematical model into the microprocessor. Now, the interface that you see over here talks to the microprocessor, and as I change these sliders, the microprocessor has got a control algorithm for calculation of the poles and zeros. So it calculates the new position of the poles and zeros in frequency domain, in S domain, and then it does a bilinear Z transform and it gets these coefficients over here, and then it programs these new coefficients into the control loop, and that's how we manage to change the crossover frequency, the output voltage, the switching frequency, and still keep the power supply stable. Okay. This is what is happening on the little board here, the power board and the the microprocessor. So first you have got a piccolo stick over here, and then you have got some TI gate drivers. You've got some NEXFET MOSFETs. There's an LDO that takes the 5 volts of the USB and converts it into 3.3 volts. And then you have a Worth inductor here. Plus a capacitor. That is a very simple buck converter with some loads that you can turn on with some P-type and N-type small TI FETs that we are using, and these are being turned on and off using the piccolo stick, and of course the mandatory LED that everybody must have on any board that you ever design. Right. That was an example of a DC-DC power supply, so let's talk about another example, which is power factor correction. We're not going to go through the details of the PFC, but PFC is one of those things whereby digital lends itself to it very well. The reason for that is that in PFC, you're actually calculating lots of mathematical equations. And as you can imagine, in digital, that's a lot easier to do than in analog. So traditionally, PFC is implemented using analog ICs and passive components, but things are changing. High performance, versatile and adaptive digital PFC systems are now a reality, and in fact, we run a workshop dedicated to this. Power factor correction pre-regulators is required to operate over the universal voltage range. Universal voltage goes from 85 volts to 265. Now, it is very, very difficult to get an analog power supply to have such a massive line voltage range and still operate properly. Also, please note that, as I mentioned earlier, the frequency changes. So you can go from 50 Hertz in certain countries to 60 Hertz in other countries. Again, in analog, it's not possible to get optimum performance when you go, let's say, to United. If you've designed your power supply to operate at 230 volts for Europe, you go to United States and you plug it in, suddenly the voltage is 110 volts and the frequency is 60 Hertz. Typically PFCs are designed at 230 volts, 50 Hertz, and that is because of the EN 61003-2 standard, which specifies a test voltage. So you design the analog one at that particular voltage and frequency, but the performance deteriorates when this voltage changes. In digital, you can measure the line frequency, you can measure the input line voltage, and you can change things appropriately. Okay, now in almost all of the analog PFCs, the shape of the demand current is created from the instantaneous values of the input voltage. What you're trying to do is you're trying to force the demand to the actual current of your power supply or any unit, your product, to be a sinusoid. Now, how do you generate a sinusoid in analog? It is not easy to generate a sinusoid in analog. So typically what we do is, if you imagine a rectified sine wave from the line, you first put the sine wave that's coming from your line through a bridge rectifier, and you get a shape like what I've drawn here on the board. And then in analog, because you don't have any mathematical functions or very limited, what you do is you pass this through a potential divider, and this will be the demand value of your current, and that goes into your analog IC. Oops. The problem is that line voltage is rarely sinusoidal. If you actually look at line voltage in many countries, the power quality is so poor that the line voltage in fact looks something like this. This shape is very common. This sort of semi-triangular with a crop top is actually very common when you look at the actual power sinusoid that comes out of a power socket. And now if you rectify this, you'll end up with this, and then you send this down the line in analog, down a potential divider, and you end up with a demand current that looks like that. And of course, if that is the demand current into your IC, that is exactly the demand current that you're going to get. In digital, you create a sine wave really quite easily. All you have to do is you say sine omega t is equal to A. And therefore it lends itself much better in creating a sine wave. Of course, there are headaches associated with this. In particular, if the line goes down or you have a brownout, then the value of this sine wave that you're generating from your digital in your digital system might be wrong, and therefore you need to look after that sort of thing. But the fact is that you can generate a sine wave and you don't have to rely on the shape of the line voltage, which is usually quite poor. In digital, a pure sine wave can easily be created in code, and that greatly simplifies the process. But of course, please take care if you're doing this, because after brownout conditions, you have to make sure that you don't end up with erroneous results. Then, in analog PFC, the square of the RMS value of the input voltage is estimated using an RC filter. And then further analog circuitry as part of the mathematical equations that you need in order to run a PFC. You need the square of the RMS value of the line voltage. This is for voltage feed forward. We do this in analog by filtering it a lot and then applying a form factor equation, because the average value of a sine wave is related by a constant to its RMS value. So you average it with filtering a lot, and then you apply the form factor equation. But that inevitably adds some second harmonic error into your system. So your demand current is asking for an extra amount of second harmonic, and you have to look after that. Of course, in digital, to calculate the RMS value, all you do is you're just sampling your input voltage anyway, you just calculate the RMS value. In analog, the harmonic content at twice the line frequency is there, and you cannot do a lot about it, and you have to take that and you have to filter it. And of course, that value changes as you go from country to country. It can be 50 Hertz or 60 Hertz. And of course, in digital, that is a digital filter, and therefore you can fix that. So as you can see, a digital PFC lends itself to high performance operation much more so than an analog one. This is an example that we use in our workshops. You can see here this is actually a low voltage analog, low voltage digital two-phase interleave PFC. And the reason we do low voltage is because obviously you cannot work on live voltages in the lab setup that we have because of health and safety reasons. However, this input sine wave can be generated by a microprocessor, and this is a line current that you can see, which is very, very nice. It actually does look absolutely beautiful. In analog, the current control is implemented using fixed passive component, and it is designed to operate only one operating point. You do lots of multiplies again in PFCs, and doing a multiply in analog is very difficult and non-linear. And in digital, additional features can also be implemented, such as intelligent phase shifting, which is what we do in the workshops, and also you can in order to improve the low load efficiency. Okay. Now, as with everything else in engineering, digital power is not without its challenges. There are advantages and disadvantages to everything that you do in engineering. Every time you get a couple of advantages, you get a few headaches. So what are digital power's challenges? The first and foremost is that people don't know how to design them. And that is why we run workshops. There are few experienced power supply designers, who also have experience of embedded system programming. We will have studied programming at university, and we would have studied analog circuit design at university. And what usually has happened up until now is that some people have gone down the hardware analog design route, and some people have gone down the software programming route. Digital power requires both skills, and there are few people who can do both at the same time. Then few programmers know much about power supplies. So again, because they've gone down the software programming route, they haven't really designed any power supplies. Neither group really likes discrete time control theory. That's the bilinear Z transforms that you need to do and in order to calculate the poles and zeros in Z domain. And people don't like doing that unless you've gone into video processing and so on. Analog power supply designers do not deal with discrete time control and very rarely do embedded systems programmers. And that's, again, one of the reasons why we provide the training. What are the other challenges? Well, there are bandwidth limitations, such as sampling group. You've got bandwidth of the microprocessor. And of course, for power supplies, you need to do a lot of processing in a very, very short period of time. But the good news is the bandwidth is getting cheaper and cheaper and cheaper all the time. Then you have got PWM frequency and resolution limits. Now, if you imagine an analog power supply, the PWM is being generated with a comparator. So you've effectively got near perfect infinite resolution. In digital, it's being generated by the microprocessor. So if you have got a slow microprocessor, or you are switching very, very, very fast, or you are stepping up or down a lot so that each PWM step is required, it represents a large voltage change, you may end up in a problem that your minimum PWM step in digital is too large, and that's a PWM frequency and resolution limit. However, again, the chips are getting ever more so sophisticated with high-res PWM on the latest chips, including the TIC 2000. They're down to 150 picoseconds per step. Now that is very, very good. Then you've got numerical problems such as quantization. Again, floating point cores are getting extremely cheap these days. You've got dedicated digital power supply ICs that have got 2, 3, 4 cores, and for very few dollars you can buy these. So that is also being solved. ADC resolution and speed. These days we have very fast 12 bits, sometimes 14-bit ADCs. You also have ratiometric referencing, whereby you put a hardware reference at a lower value and another hardware reference at a slightly higher value, and you limit the range that the ADC is operating between these two references, and that actually gives you much higher resolution for your ADC. One of the problems is that the theory is not well understood, unlike analog, whereby there's been 30 years of application notes and books and dedicated websites and tools. In digital, that is not quite there yet because it's still at its infancy. However, that's why we provide some very nice training. Current mode used to be difficult, but it's not anymore. There is digital compensation. The problem with current mode was the slope compensation. In digital, it used to be difficult to generate the compensating ramp that you require in order to stop the current mode controller getting into subharmonic oscillations. But these days in silicon, you have a dedicated ramp generator which generates the slope compensation. So we can actually do current mode control quite easily nowadays in digital. Is it more expensive? I don't know. This is something that you, as the design engineer, will have to decide. If you're designing one flyback power supply that takes to 30 volts, gives you 12 volts, and that is all it's going to do, then no, analog is possibly cheaper. Cheaper, faster, quicker. If you're doing something sophisticated, if you need several rails, you need intelligence, you need to change the control loop performance, maybe the input line range is too big, maybe the output voltage needs to vary, maybe you need to meet some stringent EMC standard or efficiency standard. You have to have very high efficiency across a wide load range, you have many rails that needs to be sequenced, then no, digital is cheaper. So this is something that you need to decide as an application engineer whether this particular technology is suitable for what you're trying to do. Typically, for very simple, low intelligence power supplies, analog will work out cheaper. For more sophisticated, high performance power supplies, digital will end up cheaper. Sometimes analog is not even an option because it's not possible to do it. So up until now, we've talked about digital power, its advantages, its challenges. So how do you go about actually designing one? Well, most people start in continuous time. They get the transfer function of the power supply. They place the poles and zeros in continuous time, and then they do something called a bilinear Z transform in order to get the coefficients that they need for the digital control loop. Then that goes in a linear difference equation, and the microprocessor will then run the linear difference equation in order to stabilize the power supply. You can do this with various tools or by hand. I wouldn't recommend you doing it by hand. So in order to make your job really easy, what we have done is we have designed a very sophisticated power supply design tool called Biricha WDS. Now, arguably, this is one of the world's most sophisticated power supply design tools. You've got a lot of features and it designs both analog and digital power supplies. It automatically calculates the poles and zeros as well as component values for the most popular topologies. Sophisticated control algorithms stabilize digital power supplies with automatic coefficient calculations in floating point 32-bit and 16-bit. Not only that, the software takes into account the time delays that are introduced in a digital power supply and compensates for that. So if you ask for 50 degrees of phase margin, you really will get 50 degrees of phase margin. It's got the special features which allow the manipulation of digital compensated coefficients for a host of microcontrollers. And for analog power supplies, it also designs with TL431 and LM431 with the optocouplers, which you can characterize, and we teach that in our analog power supply design workshop for isolation. And then you can have simulation in time domain, in frequency domain, and ability to superimpose the real measurement on the simulated data. I will do that shortly in a demo. So to actually show you this software, I'm just going to go to Biricha WDS, which is here. And you can see here that I have designed a power supply using this software with a crossover frequency of 10 kilohertz and a demand phase margin of around 50 degrees. So the green trace here is the simulation using WDS, and the black trace is the actual measurement which I've done with the Bode 100, and I can superimpose these two on top of each other. And I can compare the two, and you can see that the desired values where on the green trace are 10 kilohertz and 49 degrees, and the real measurement is 10 kilohertz and 53 degrees. So it is a very nice match between what you have designed for and in fact what you have measured. So now if we go back to the actual setup that I have got, what I'm going to do now is I'm going to really measure it with the network analyzer, and I'm going to show you that I've got a crossover frequency of 10 kilohertz and a phase margin of around 50 degrees. So let me just quickly close this down, and I run the Bode analyzer suite. Now this is now connecting to the Bode 100. I just need to open the setup file. I recently opened it, there we go. Okay, what you see now is the previous measurement, and now what I can do is I can do a live measurement. But first let's have a look at the circuit. This is the TI Piccolo board that we use in the workshop. This is just a power stage, and the microprocessor on this control card is controlling the power stage. Then I have got an injection resistor over here, and I have connected my Bode 100 to the injection resistor. I am injecting a sinusoid. I'm injecting a signal into the across the injection resistor, and then this unit will measure the gain and the phase, and it will plot them for me. So let's start the measurement. And you can see that I've got an almost perfect match. Now, if I go here and I type in 0 in order to get my crossover frequency, I have got a crossover frequency of 10 kilohertz, and I've got a phase margin of 48 degrees, and I expected 50 degrees, so it's almost a perfect match. And now we've got a live loop measurement of a digital power supply, and you can see that it is performing very well indeed. So that is in frequency domain. The next thing that we're going to do is we are going to look at its transient response, and I'm going to do that with the oscilloscope. So I'm going to disconnect the Bode 100, and I'm going to connect the oscilloscope and do a proper transient response measurement. Okay, so I've connected channel 2 to the output voltage. I have set the output voltage into AC coupling, and I have set it up so that I can see the transient as I do a switch. So if I just change the mode so that it actually grabs one, and you can see right now that you have got this beautiful transient here. You can see that there is no ringing. That means that I've got plenty of phase margin, and you can see that it dips a little bit and then it moves back up again. Now this particular scope has got a very nice set of power analysis tools, and I have set power analysis to transient response, and you can see that with this now, with these cursors, I can very easily measure the time to peak, settling time, and so on. The settling time at the moment is measuring around 75 microseconds with no ringing, and I can also use the cursors in order to actually measure by hand if I don't want to use that. So if I again do another trigger, this is a trigger, and with my cursors I've got around 75 microseconds, and let's see if I can get this one up as well, and you can see from here that the dip in voltage is actually around 45 millivolts. This has actually got a very nice little feature that allows you to connect to the network, and I've done this already. So if I just go to my network, you can actually see, I should be able to display for you the full screen so that you can have a very nice view of the actual measurement. There you go. Here you've got your measurement. You've got a undershoot of about 45 millivolts, and you've got a settling time of about 74 microsecond, and that is done, gets updated once every second, I think, directly via my network, and these are the cursors that allow me to very quickly and very easily do the measurement. There we go. It's a very nice and stable power supply. So what we have seen so far is advantages and disadvantages of digital power. We have shown you some very nice demos. In particular, we showed you a self-tuning a digital power supply, and then we used a bigger power supply. We measured the loop. We showed that you can stabilize the power supply beautifully in digital, and we managed to get a very nice crossover frequency of 10 kilohertz and a phase margin of around 50 degrees. And then we used the oscilloscope in order to do a very beautiful transient response measurement, and we saw that we get very nice transient with no ringing and very little dip. So to conclude then, digital power will be a significant player in the future of power management for the reason that we discussed earlier. In many applications, digital power has advantages over its analog counterpart. Designing digital power need not be difficult. We provide in-depth hands-on workshops, excellent development software and libraries, and consulting services. It just remains for me to say thank you very much for your time, and thank you for listening, and I hope we can see you in one of our workshops.